Good morning, everyone, and welcome to the first lecture of the second course or second session in concrete technology. Our lecture today will be in English, not in Arabic, and I'd like you to be prepared for all the lecture will be in English. So from now on, if you have any question, we can talk about it and answer all your questions during the lecture on a Tuesday morning. So, our lecture is about the properties of hardened concrete. Previously, we have all the chapters talking about the ingredient of the concrete, like cement, types of cement, aggregate, and finally we talk about the fresh state of concrete, mixing, placing, and curing of concrete. Now, after the curing, the concrete will get harder and harder by time. And during this stage, the main properties of concrete in its hardened state include strength, permeability, shrinkage, which is the volume change of concrete, creep or extensibility, elasticity, and thermal movement. And finally, we have the durability, which is the resistance of concrete to corrosion, erosion, weathering, and chemical action and wearing or abrasion. First of all, we will talk about the strength. The strength of concrete can be resistant to different kind of forces. The first one is the shear force, or the tension or tensile force, and the flexural and compression. So this is the main forces that act on concrete while serving in concrete buildings. The shear strength can be defined as the strength of a material or component against the type of field or structure of failure when the material or component fails in shear. A shear load is a force that tends to produce a sliding failure on a material along a plane that is parallel to the direction of the force. In this figure, you can see different types of forces acting on a material. In particular, we're going to talk about the shear stress or the shear forces, which is, as you can see here, it's two forces acting on the same plane in opposite directions. So this force acts on the this direction, and the other force acting in opposite direction, which causes a failure in a line shape between the two parts of the material. Also in this figure, we have this figure talking about the tension stress, which is also two different forces acting in the same plane in opposite directions, but they are acting on the same line. And here we have a plane between the two forces. But in tension force, we have two forces acting on the same line, causing a failure in different planes, while in shear we have only one failure plane. Also, this figure explains the compression stress, where two forces acting on the same line but in the same direction. So we have this force here acting on this direction, and the other force acting on the same direction, causing a failure in the material in different planes. The shear force can be estimated by different international standards, and one of them is the AS 3600, which is the Australian standard one, which require the concrete shear strength to be calculated or estimated according to these formulas. So for beams, we have the shear force F sub CV is equal to F sub C to the power 1/3. And this value should be less than 4 MPa for beams. So for example, for 20 megapascal concrete, the F sub CV, the shear strength, is equal to the 20 of power 1/3, which is equal to 2.7 megapascal. And this value is lower than 4 MPa. While for slabs, we have different formulas or different equation, and the F sub CV is equal to this formula. So for slabs, we have this formula, as we said before, and the beta H, this factor, is the ratio of longest to shortest dimension of the slab or the loaded area. For example, if we have a slab with dimensions 4 by 4, the beta H will be equal to 1. And the concrete strength of 20 megapascal for compressive strength, then we can estimate the shear strength by this formula, and it will be equal to 2.28 megapascal, which should be less than 0.34 20 to the power of half, which is equal to 1.5 megapascal. And this figure explains how the shear cracks can be seen in different structural members. For example, we have the beams here, and you can see this crack with like angle nearly 45 degree. Which is caused by shear, but in a tension failure. And we have also a failure here in this beam with an angle nearly to 45 degree, but in different cause. This one is caused by tension failure, and this one caused by a compression failure. And both of them have the shear failure at the end of the day. And also for columns, for concrete columns, we can see different types of failures depending on the conditions of the structural member and the force acting on this member. So for shear, the failure will be like this, and you can also see a failure mode with nearly 45 degree angle. And this picture, you can see the failure of the concrete columns. And this one is a shear failure, and this one is compression failure, and it can happen maybe on the bottom of the column or the top of the column. And this failure is called the buckling, and we will take about these different types of failure later on. Now we are gonna move to the different type of strength, which is the tensile strength. And as you know, the concrete can resist the compression or the flexural in a good way, but in the tensile strength, Usually in the design structural codes, the tensile strength of the concrete is neglected because the concrete cannot resist a tensile forces that much. So, as I said, the design codes usually neglect the tensile strength. But in some cases, we need to calculate the tensile strength. For example, in hydraulic structures, we need to know in which case the concrete will start cracking, because the tensile forces acting on a concrete, it can easily cause a micro crack in a hydraulic structures, and this is very critical condition, and we cannot neglect it in this case. So, tensile strength cannot be calculated or tested directly, and that's why we have indirect tensile strength. The indirect tensile strength is also can call the Brazilian test or cylinder splitting test, and you can find this type of test in different testing codes. For example, the ASTM code or the BS, the British code, or the Australian code, and all of them is nearly have the same test procedure. And for this purpose, we need to prepare a concrete cylinder with 300 millimeters long by 150 millimeters diameter, and we can put it on the testing machine in this position, and we can use a compression machine, applying the force on the top and the bottom of the specimen, and then after applying the load, we have the final test result recorded in the machine, and the specimen will split it in two halves, like in this picture. After getting the test result of the indirect tensile test, we have this formula of this equation we can use to calculate the indirect tensile strength, where T is the indirect tensile strength in megapascal, and the P is the failure load recorded by the testing machine, and L is the length of the specimen, which is 300 millimeter, and D is the diameter of the specimen, which is 150 millimeter. Now we're gonna move to the flexural tensile strength, or the modulus of rupture. The modulus of rupture is determined from a 4-point bending test, as explained in this figure, where a prism specimen test sitting here in the testing machine in two supports, and the load is applied by 2 points. Then finally we have a 4-point loading test. During the test, the extreme fiber from the bottom will have a tensile forces acting on it, and the compression forces will act on the top fiber of the concrete specimen. And this test is very important when concrete is used for the pavement of the airports, where the impact load from the airplanes